Year 13, Chapter 9, Further Differentiation, Lesson 3, Differentiating the Trigonometric Functions. We're going to start by learning how to differentiate sine x by first principles. Now, one crucial thing that we need to mention is that if you are differentiating a trigonometric function, you must ensure that you are working in radians. Results will not be correct if you are not working in radians. Now, let's start by identifying 2 points on the graph of y equals sine x. You can see a small portion of the graph here. I'm going to identify a point P and I'm going to identify a point Q. These are general points. Now, let's give P an x-coordinate, which we'll call x, and Q is a short distance away from P, and it's got an x-coordinate of x plus h. So we're saying that this gap here between P and Q is a distance of h horizontally. Now, what about some y-coordinates? Well, the function is y equals sine x, so the y-coordinate here is going to be sine x, and the y-coordinate of Q is going to be sine x plus h. Now, our next step is to draw a chord joining point P to point Q, like that. So, what do we know about differentiation by first principles? Well, we know that the gradient of the function dy by dx is equal to the limit as h approaches 0 of the gradient of the chord PQ. And you may have written out previously this statement, f of x plus h minus f of x, which would of course be the change in y coordinate, delta y, difference in y coordinates, over x plus h minus x. And this is, of course, your difference in your x coordinates. And that's a more generalised version for the principle behind differentiation by first principles. But here, of course, our f of x is sine x. So we have sine x plus h minus sine x. So again, hopefully you can see that that's the change in y coordinate here. And again, we're dividing by x plus h minus x, which we'll simplify in a second, which is the change in x coordinate. So it's this distance here and here. And of course that gives us the gradient of the chord PQ. Now, what can we do to simplify this? Well, we can use an identity to expand this. We know that sine x plus h will be equivalent to sine x cos h plus sine h cos x. So we have a compound angle identity here. Let's substitute that in. And also in the numerator we still have minus sine x. The denominator simplifies to simply give us h. Now, we have to remember here that h is a small value, so we can make use of the small angle approximations here. So we know that sine h is approximately h, and cos h is approximately 1 minus a half h squared. So again, reminding ourselves of the small angle approximations. So let's input this information. So we have the limit as h approaches 0 of. So we have sine x, and then instead of cos h, I've got 1 minus a half h squared, plus cos x, and then instead of sine h, I've just got h, and then we've got subtract sine x. And of course, there is a denominator of h here. Now, let's have a look at what we can say next. So we can see that there's a sine x multiplied by 1 here, and then there's a subtract sine x here. So those parts will disappear. And we're then left with minus a half h squared sine x plus h cos x, all divided by h. So we're going to make sure we divide by h next, which gives us the limit as h approaches 0 of negative a half h sine x plus cos x. Now, allow h to approach 0. Take the limit as h approaches 0, and you can see that this part here will approach 0 as h approaches 0, whereas the other part of this, which is simple cos x, is unaffected by changes to h, so will be left. So this gives us cos x as the answer. And don't forget what we were actually doing here. We were finding dy by dx, where y was equal to sine x. And we've discovered, using first principles, that if you differentiate y equals sine x, then dy by dx is equal to cos x. So the sine function differentiates to the cosine function. So here we have a sketch of the graph y equals cos x. Notice its negative gradient between 0 and pi. So let's apply what we know about differentiation from first principles. Dy by dx is equal to the limit of the gradient of the chord PQ as h approaches 0. And I'm going to set the calculation up as cos x plus h minus cos x. Doesn't matter as to which value is bigger. Really, it will all work out in the end. And denominator x plus h minus x. So change in y coordinate divided by change in x coordinate, being consistent as to which coordinate comes first. We've done the coordinates of q, subtract the coordinates of p for this. Now, we need to use an identity again for cos x plus h. So let's use our double angle formula again. Cos x plus h is cos x, cos h minus sine x, sine h. So this then becomes our numerator. And of course we have minus cos x, which was originally in the numerator. And our denominator, of course, is simply h. Now, remember, h is small, which allows us to use the small angle approximations, that sine h is approximately h, and cos h is approximately 1 minus a half h squared. So, we have the limit as h approaches 0. I'm going to replace cos h with 1 minus a half h squared. And I'm going to replace sine h with h, and then of course we have minus cos x at the end. And the denominator is still h. Now, as we saw with the derivative of sine x, we're going to get a cancellation. Multiplication here will give us cos x, and then we have a subtract cos x. So we can take that out. So we have the limit as h approaches 0 of negative a half h squared cos x minus h sine x all over h. Now let's divide by h before we take the limit as h approaches 0. And we're going to end up with negative a half h cos x minus sine x when we divide each part by h. So now we're going to allow h to approach 0, which means that because there's a factor of h here, this will approach 0, but this part here which has no h feature, will simply remain as negative sine x. So this tells us, very interestingly, that the derivative of y equals cos x is negative sine x. So, in general, what do we know so far? We know if y equals sine x, then dy by dx is equal to cos x. And we know that if y equals cos x, then dy by dx is equal to negative sine x. Now, we sometimes like to generalise a little bit further. So if y is equal to k sine x, remember that this k is just a multiplicative factor, so dy by dx will equal k cos x. And similarly, if y equals k cos x, dy by dx will simply equal negative k sine x. So as a starting point, it's really important that we memorise and learn these results here. So we're now going to learn how to differentiate y equals tan x. And we're going to remind ourselves that tan x can be written as sine x over cos x using a well-known trigonometric identity. And what do we have here? We have a quotient. We have u in the numerator, which is sine x, and we have v in the denominator, which is cos x. So we can use the quotient rule. Let's set everything up, and we now know how to differentiate sine x, gives us cos x. We know how to differentiate cos x, gives us negative sine x. So all we have to do is remind ourselves of the rule, the quotient rule. Dy by dx is equal to v multiplied by du by dx, subtract u multiplied by dv by dx, and remember, it's a bit more complex than the product rule. Everything has to be divided by v squared at the end. So v multiplied by du by dx first of all, cos squared x. Cos x multiplied by cos x simply gives us cos squared x. And what about u multiplied by dv by dx? Well, that's sine multiplied by minus sine, so it gives us minus sine squared x. Now there's already a subtraction, remember, so we get minus minus sine squared x. Now, what next? We need to check we've got the denominator in place. Well, the denominator is v squared, which is the square of this, so it's cos squared x. Now, look at the numerator. The numerator simplifies to cos squared x plus sine squared x. And we know exactly how we're going to simplify that in a second. The numerator simplifies to 1 using well-known trigonometric identity. So we have 1 over cos squared x. But we know from our knowledge of reciprocal functions that this is the same as sec squared x. So we know if y equals tan x, dy by dx is equal to sec squared x. And that's another important result. It's important for you to be able to carry out this process. So you need to make sure you learn and you're confident about how to differentiate tan x using the quotient rule, and it's important that we understand and know the result that y equals tan x differentiates to sec squared x. So we can generalise this a little bit further. If y is equal to some constant k multiplied by tan x, then dy by dx will simply equal k sec squared x. Now we will look at more complex derivatives involving trigonometric functions in just a moment. So as always, we're going to explore the chain rule first of all. So here's an example to start off with. Y equals sine 3x. Can you see the composite function here? We have 3x as our inner function, and then we're taking the sine of this. Now, let's have a look at the chain rule in its long format. So this is where we need to identify that u is equal to 3x, and we need to write y in terms of u. Y is equal to sine u. What is du by dx? It is 3. And what is dy by du? It is cos u, as we now know from our work in first principles. Remember the chain rule? dy by dx is equal to dy by du multiplied by du by dx. So dy by du is cos u multiplied by du by dx, which is 3. So our answer is then 3 cos u, but remember we know that u is the same as 3x, so we can rewrite this as 3 cos 3x. Now, look at the question. Look at the answer, the derivative, I should say. Can you see how we could have done this using the quick chain rule? So we're starting with y equals sine of something, sine of 3x. So we know that a sine function differentiates to a cos function, so this will differentiate to cos of 3x. But what do we need to do? We need to multiply by the derivative of the inner function, which is 3. And there we get to 3 cos 3x straight away. So let's just say that again. We know that sine of something, in this case the something being 3x, differentiates to cos of something, cos of 3x. And then of course we finish by multiplying by the derivative of the inner function. And that's how we can apply the quick chain rule. So here is a set of 6 examples for you to have a look at. Now, you can either pause, have a go at each of these questions yourselves, and then check your answers, or work through the questions with the video. Now, in each case, you're going to differentiate each of these using the quick chain rule process. So now is the moment to pause if you want to try the questions by yourself. Question 1. Look at the inner function, the 5x over here. Now the 2 at the beginning is just a multiplicative constant, so dy by dx is equal to 2 here. Now sine functions differentiate to cos functions, so sine 5x differentiates to cos 5x, but of course we need to make sure we multiply by the 5. Remember, it's the overall function that's being multiplied by the 5, not the 5x within the cosine. So the final answer to this is going to be 10 cos 5x. Question 2. This is a cosine function overall, and the inner function is 2x plus 3. So dy by dx, we know that a cosine function differentiates to negative sine, but we need to multiply by the derivative of the inner function, which is 2. So dy by dx is negative 2 sine 2x plus 3. Question 3, this is a sine function overall with an inner function of x squared. So we know sine differentiates to cosine, so it will differentiate to cosine of x squared, but we need to multiply by the inner function, which is 2x. So final answer, dy by dx is 2x cos x squared. Now I've put in both cases the x squared in brackets because I want to make it really clear this is not sine squared x, this is not sine of x all squared, it is very specifically x squared and then we take the sine function, so please don't get mixed up between the two. Moving on to question 4, this is a cosine function. There is a constant of 3 at the front. So dy by dx is equal to 3, but cosine differentiates to negative sine, so we have negative sine 1 minus 5x. The inner function is 1 minus 5x, so multiply by negative 5. So we end up with dy by dx is equal to 15 sine 1 minus 5x. Now, the last two examples involve tan. It's an overall tan function with an inner function here of 2x in question 5. We know that tan functions differentiate to sec squared of whatever the inner function is, which is 2x, but we need to multiply by the derivative of this inner function, which is 2. So final answer, 2 sec squared 2x. And the last example, again, it's overall a tan function. So dy by dx will be sec squared of 3x squared minus 1, which is the original inner function. Multiply this by the derivative of this inner function, which is 6x. And this takes us to the final answer of 6x sec squared 3x squared minus 1. A lot of detail in this last question. So check your answers and make sure that you are in agreement with these and you understand how we've got to these answers using the quick chain rule. So in general, if y equals sine of something, so sine of some inner function, so we have a composite function which is a sine function overall, then dy by dx will equal cos of this function, f of x, but we also then need to multiply by f dash x, the derivative of the inner function. And remember, it's the whole thing being multiplied by f dash x, not just the f of x or something like that. Now, what happens if y equals cos of some other function, f of x? So we have a composite function with cos as the outer function. Well, then we know that dy by dx is equal to negative sine, because cosine differentiates to negative sine of f of x. But again, multiply by the derivative of the inner function, which is f dash x. And lastly, if y equals tan of f of x, then dy by dx is equal to sec squared, because tan differentiates to sec squared of this inner function f of x. But again, we need to multiply by the derivative of the inner function because that's how the chain rule works. So multiply by f dash of x. So 3 important results to make sure you know and understand. So we'll just finish by highlighting these 3 results. Make sure you've got them written down clearly. So we're just going to finish off with a few examples which involve a mixture of the functions that we have met so far, exponentials, trigonometric functions, natural log functions, and they're all composite functions. So we would differentiate each of these using the chain rule. And we're going to aim to use the quick chain rule to differentiate each of these examples. But we must identify what type of examples we have, because they all involve powers at some point. They all involve trig functions. They all involve exponentials. Some of them involve natural logs. And we need to understand what is the overall function and what is the inner function when we're using the quick chain rule. So in the first question, you can see that there's a cosine function, but it's not the format cos f of x. This function here is cos x, and it's being raised to a power of a half. So this is in fact a power function. And when we differentiate it, we need to differentiate it accordingly. So dy by dx, multiply by the power, reduce the power by 1, and then multiply by the derivative of the inner function, which means multiply by the derivative of cos x, which is negative sine x. So what's our answer? It's -1/2 sine x cos x to the -1/2, which you could write in the denominator as the square root of cos x if you wanted to. So another way of writing this answer would be negative sine x over 2 the root of cos x. But what was crucial here was identifying that this is actually overall a power function, and it's the inner function that is a trig function. Let's look at the one next door to this, y equals sine squared 4x. Now again, there's a trig function, but there's also a power here. What's happening? Let's break it down. We've got sine 4x and it's being squared. So this is in fact a composite function where the outer function is actually a power. So dy by dx, multiply by the power of 2, reduce that power by 1, so it drops down to 1, and then multiply by the derivative of the inner function. What's the inner function? It's sine 4x. So you're having to use the chain rule again, and it should become like second nature. What does sine 4x differentiate to? Well, we know it's a sine function, so it differentiates to cos 4x, but we've then got to multiply by the derivative of the inner function, which is this 4x here, so multiply by 4. So at the end of all that effort, the final answer will be 8 sine 4x cos 4x. There's no need for the brackets here, really, just trying to provide some clarity as to the different components of this. So here's the final answer. Now, this red question. What is the overall function? There's an exponential and there's a cosine involved, but the overall function is a cosine. So the inner function we can identify as e to the x plus 3. Now, dy by dx, cosine functions differentiate to negative sine, so negative sine e to the x plus 3. Multiply by the derivative of the inner function. What happens if we differentiate e to the x plus 3? We just get e to the x. 3 differentiates to 0. So the answer is negative e to the x sine e to the x plus 3, and we need to write this out in this format here. So on the right hand side in blue, y equals 3e to the sine x. There's an e, there's a sine, but it's overall, have you worked it out? It's exponential overall. It's e to the f of x here. That's what we have. So dy by dx, let's work it out. E functions differentiate to themselves. The 3 is just a multiplicative constant, so it's going to be 3e to the sine x, but multiplied by the derivative of the inner function. The inner function is sine x, differentiates to cos x, so here we have our answer, 3e to the sine x multiplied by cos x. Now, final question, left-hand side, bottom left-hand corner here. Y equals ln of tan x. Can you see that this is a log function? So it's ln of f of x, where f of x is our inner function and the inner function is tan x. So dy by dx, we know log functions differentiate to 1 over, or reciprocals, so 1 over tan x. Multiply by the derivative of tan x, and we know the derivative of tan x is sec squared x. Now, I think this could do with a little bit of tidying. So let's remind ourselves that 1 over tan x is the same as cot x, or cos x over sine x. And then sec squared x is 1 over cos squared x. So what will happen here is a cos x will cancel with one of the cos x's from cos squared, and we will be left with, as a final answer, 1 over sine x cos x. So we had a log function here, and we had an exponential function in this question. So we have the quick chain rule. We need to identify the outer function first of all, and then identify the inner function. And then we can apply the rules for the chain rule very efficiently and very, very quickly. So we're now going to quickly finish off by practicing using the product and quotient rules when we're differentiating trig functions, or a mixture of trig and other types of functions. So have a look at these two examples first of all. You should be able to see straight away that in both cases we are dealing with product. So we're going to use the product rule for both. So let's start with the left-hand example. So I want one part of my product to be u. The other part is sine x. Let's differentiate both. Du by dx is 1 and dv by dx is cos x. You must start to become really efficient with setting up your derivatives. So let's apply the product rule. U multiplied by dv by dx plus v multiplied by du by dx. And let's put everything together. So we have these two multiplied together and we have these two multiplied together. So u multiplied by dv by dx gives me x cos x, and v multiplied by du by dx, well, that's just sine x. So here's my final answer, and there's nothing to factorise here. It's quite a simple example. Second example, you may wish to pause the video and have a go at this yourself, or you may wish to follow the video. One part of the function u is e to the 4x and the other part is cos 2x plus 1. Now in both cases we're also going to have to use the quick chain rule to differentiate the two separate parts. So du by dx, it's an e function, so it differentiates to e to the 4x, but we need to multiply by the derivative of the inner function, which is 4x, and the derivative of that is 4. So we have 4e to the 4x. Now for v, dv by dx, we can see it's a cosine function, so it will differentiate to negative sine 2x plus 1. But we need to multiply by the derivative of the inner function, and the inner function is 2x plus 1, which differentiates to 2. So we have this. So we have the product rule written out already. So dy by dx is u multiplied by dv by dx. So let's start putting all of that together. So that's negative 2 sine 2x plus 1 multiplied by e to the power of 4x. And we then want to add on v multiplied by du by dx, which we have over here. So that gives me 4 e to the 4x, and then of course cos 2x plus 1. So we can factorise a little bit. We can take out a 2 and an e to the 4x, and what are we left with? Negative sine 2x plus 1 plus 2 cos 2x plus 1. So for clarity, I might just reverse the order. So we have 2 cos 2x plus 1 minus sine 2x plus 1 here to finish off. So have a look at the final pair of examples, and you should notice straight away they are both quotients. So first example, u equals cos x, v equals x. So can you all see, hopefully, the u over v format? Du by dx we now know is negative sine x, and dv by dx is equal to 1. Now let's remind ourselves of the quotient rule, which tells us that dy by dx is equal to v multiplied by du by dx. And we then need to subtract from that u multiplied by dv by dx, and make sure that the whole thing is divided by v squared. So v multiplied by du by dx first of all gives us x multiplied by negative sine x, And then we're subtracting from that u multiplied by dv by dx, which is simply cos x. And then just have the whole thing divided by x squared, which is v squared. And you could divide through both parts of the numerator and separate it into two parts, but there's no real need to do that. And this takes us on to, finally, our last example, which is again a quotient. Now, u equals ln 2x, v equals sine x. Careful here, because there will be a number of people who are tempted to forget how to differentiate ln of kx and say that the answer is 2 over x. It's not, it's just 1 over x. And you need to make sure you remind yourselves of that rule, which you've learned about in a previous lesson. If y equals ln of kx, then dy by dx is just 1 over x. Now, if you've forgotten, you can use the quick chain rule here. Look at the fact that it is an ln function with 2x as its inner function. So we would differentiate to 1 over 2x, but we need to multiply by the derivative of the interior function, which is 2. So the 2's cancel, leaving us with 1 over x, and you see the result again. Now, what about dv by dx? That's easy, it's cos x. Now we have the rule written out here on the left-hand side, so let's just apply it. dy by dx is v multiplied by du by dx, so that is 1 over x multiplied by sine x minus u multiplied by dv by dx, which is cos x multiplied by ln 2x. It's easiest to sort of write it out like this, or to put some careful brackets in just to indicate the different functions very, very carefully. And this is all over v squared, which is sine squared x.